It's a great honor to have here Professor Daniel Keim from the University of Constance in Germany, an international expert on visual analytics, who will actually tell us quite a bit about visual analytics for the analysis of big data. He will be our keynote speaker, and then we will have the second speaker, and then the brief introductions to the posters. So Daniel, please come up and tell us a bit about visual analytics.
Yeah, thank you very much for the introduction. It's an honor to be here. As you can see, I'm from Europe, and I expected to be together with many business people. I was giving a keynote talk last week at a conference, the Big Data Analytics conference in Germany, and like mostly business people, and like everybody was wearing a Y, almost everybody. A few people from university didn't, but most of the people did. So I thought I'm here again in a similar audience, but I'm not, as you can tell. So I'll take it off later. I thought I'd keep it on for the talk. I think I'm the only one with a tie in the room, which distinguishes me from all the rest. But so if you come to give a talk at a German business conference, you better wear a tie or a suit and so kind of stuff. At university, I don't. So it's like, but here I did. So you can enjoy it, hopefully. So I will be talking about visual analytics, and visual analytics has to do with big data. Actually, I was working on this topic since about 20 years ago. When I started, I actually was doing my PhD in databases. And when I was dealing with big databases, I was really feeling there is need for exploring the data in a different way. SQL queries are not the right way of dealing with big data. And at that point, I called it visual data mining, if you've heard that term. And it developed into the term visual analytics. And the big data term came out a lot later. Like basically, I think big data was around already much longer, but it was really getting popular by the McKinsey report in 2011, which is now about 3 years ago, the term of big data and all the big benefits that McKinsey promised, and industry is jumping on it. So I think this is a hype, and you know the hype cycles, how they go, and I'm not explaining any of this. You probably have read it and seen it many times. What I like is this chart here, where it's getting more concrete. It's from last year. It's telling you how much data is generated every minute. And as you can see, some of the data sources really have millions of records every minute. And if you count on a whole year of data, you get to quite large numbers. The largest are probably in the internet security, IP packets, IP flows domain, where you have billions per minute. So, and I'm going to talk about that later. We already have heard that data mining works in some cases quite well. So automated data analysis, and that's what I'm now calling it in the following, seems to work well for big data, which is a good story, right? It's good news. But if you look closely, you find out it's only working under certain preconditions. And let me explain what I mean. In many cases, it really works great automated analysis if the data has certain properties. And the properties are actually in many applications, many real applications, rarely met. So what are these preconditions? The data needs to be clearly structured, the semantics needs to be well defined, and the data needs to be complete, correct, not changing over time. And as you know, this is true only for very, very few applications. And in case any of these points is not clearly defined, like the semantics, if you deal with text data, semantics is obviously not clearly defined in many cases. The structure is often not clearly defined, and the data is rarely complete or correct. So all these properties are not met, and then it's not always easy to apply automated algorithms because they may be misled completely. There's an additional problem that I want to outline, namely that in many applications, even the problem is not well defined. You don't know what you're looking for. And this is even harder. If you don't know what you're looking for, it's a lot harder to define an algorithm. There's no way to define an algorithm for searching for something that you don't know what you were searching for. So I think this is really the core why visual analytics is really needed. And let me explain this by a few examples, data examples that I've worked with personally. First thing, network security, IP flows. And I always kind of say what the data is and what the task is, and you could come up with different data sets and different tasks in each of these domains. It's just sought to be an example, and I've worked with these, so I can talk a little about it. So if you go for network security, you work with IP flows. If you don't know what IP flows are, it's basically a number of related IP packages that you already aggregate. Because if you work with every packet, it's really too much. And then it's like hard to work with anyway. So you already aggregate them into flows, and this is done on the Cisco routers, so you get that quite easily. And if you want to detect novel viruses, and we work with Symantec in that application on a bigger EU project, it's really hard to do that fully automatically. Why? Because a new game may have similar patterns than what you get from a new virus. So how should you decide? Actually, it's only people that can decide that in the end. So there need to be people involved in that application. But having said that, you need automated algorithm to detect what is unnormal here. You can't shut it down automatically, but you have to detect it by automated means and then have a human investigate it to quickly make the decision, oh, this is a new virus, we should send out a new virus definition to everybody in the world, downloading it hopefully immediately. Or to say, okay, this is valid traffic, we don't need a new virus definition because there is this new whatever happening out there in the internet that should be allowed to happen. Second example, and actually we had this already in one of the previous talks, and very nice that we had got already a feeling of fraud detection, credit card or whatever type of fraud. I've worked with both credit card and phone call fraud. And the task detection of that fraud, great if you have a sophisticated algorithm that helps you. But what to do if you have a higher score? Shut this down? Don't allow this transaction to happen? Which is done in some cases. It may have happened to you in credit card that you didn't got your credit card transaction accepted, which is not nice if they completely block it, if it's a valid one. You don't like that as a customer. And the credit card company doesn't like it if it's from an important person. You don't shut down a transaction of your CIO. You do it only once because then you're fired, right? So that's kind of, you don't want that to happen automatically. So even if you have these nice scorecards that give you a risk value, a human has to investigate in many cases before you make final decisions. So there is no way, and we actually saw a number of charts. He was using a lot of visualizations in his presentation, so actually it's not that far. To make the decisions to act on it, you again need visual investigating. The human needs to be involved, and that's basically the story. Third example, business analytics. If you have customer records, if you want to define new customer target groups, very difficult to do fully automatically because there is application knowledge. The computer may suggest certain groups, new target groups or whatever, but you don't want the computer to make that decision. You want to know why this group and not that group, different partitionings, different customer groups, because this is having a direct impact on your business. And going for the wrong target group may be a big loss in the end if you don't decide it as a human. There's lots of semantic knowledge that goes into this process, so the computer won't have an algorithm to do it. Having said that again, and in all of these, you need automated analysis. I'm not saying you should get rid of it, but you need the human to be part of it. Final example, molecular biology. If you have patient DNA records, and we have this data now readily available in many applications, if you want to find the functional root cause analysis for an illness, there is no chance, and we had an example from the medical domain already, there's no chance to do it fully automatic. There is so many things that we don't know yet. By at least my lifetime, I don't expect this to be fully automatically possible. And I see somebody nodding here who knows a lot more about probably this domain. I'm still learning in this domain. But the more I learn, the more I know that they know very, very little. I guess few months ago I said they probably know 1% of the dependencies and knowledge in DNA. By now I think they know less. The more I know, the more I have the feeling they know less. But it's like my feeling. The experts probably tell you different stories. But it's really, we know so little, so it's very hard to do that by algorithms. So the human is kind of really core, like pathway analysis. If you want to do that, there's so many pathways. If you draw them, it's filling all the walls in this room for even one single process in the human body. It's so complex. And this is only what we know right now. A few years from now, it will be a lot more. So there is no simple way. We need algorithms, but at the same time, we need the human knowledge and intuition to do it. So I hope I've convinced you that automated analysis is not enough. And actually, just to give you a new chart here, this is February 2014, the new Gartner chart. And what was surprising to me, that all the companies that deal with visual analytics are up here, like Tableau software, ClickView, SAS with their Jump software, TIBCO. These are all visual analytics companies that are all up here in the quadrants where you want to be as a company. So this is currently, by Gartner, not by me, considered very, very important. And these are leading. These are the leaders and visionaries, right? This is what they call them. And that has a reason. Why is visualization needed? I hope I've convinced you. You need visualization in addition to the automated analysis in order to identify the structure based on user knowledge. And there's no way of bringing all your knowledge, all the human knowledge, into the computer. Why? Oh, there are many reasons for that. One is that you wouldn't be able to specify it all. But another reason is that you wouldn't even want to specify it all. Like one of the reasons why one of the traditional optimization problems, like timetable planning for like classes and so on, is still done by humans, helped by algorithms, of course, is that you would never specify all the constraints. Like, would I specify that if my colleague X, whom I don't like, gets these positive slots, like always, like in the middle of the day, never the morning slots and so on, I would certainly complain if colleague X gets it, while with colleague B, I would never complain, right? Because I like him, and so if he gets the good ones, I am positive about it. I would never give these constraints to anybody. And they may change any day because I may not like somebody or may like another person. So these constraints will never be in the system. So the algorithm can't know that. But the person who deals with it every year, they know all the constraints. They have it in their mind. Like, I know colleague X is always complaining. I better give him the slots right away, or the good rooms, or whatever. So this is knowledge in the human you will never have in the computer. And there's plenty of this. And this is only one of the reasons. Bridge the semantic gap, bring in the knowledge that is not in the computer, help with incomplete, incorrect, and changing data, and, of course, understand the problem, generate hypotheses, and define the problem in the end. And visual analytics can also help to steer the analysis process in dealing with massive data, which is helping you to do the local optimization better than the computer can do. And this is now dealing with like NP-hard problems where the computer always does some heuristics, makes some decisions based on whatever kind of numbers, and the human knows, oh, you better go this way. This way doesn't make sense. And the human can steer and help and do the crucial decisions. The point is, how do we get the human, empower the human to do the right decisions? And now I have a bad news that you probably didn't expect. Visualization of massive data doesn't work. Right? You know that. You have maybe 2 million pixels on your screen. Maybe you have 10 million pixels on your screen. But even if you do, I tried to push the resolution of this beamer, but it was like fixed at about 1 million pixels. There's no more on this kind of, like it's less than 1 million actually. But if I show you some pictures like a network visualization, and this is already quite a lot of data, and this is a tree map, by the way, partitioning the internet into subspaces and so on. You don't see the important information here. It's too low resolution. It's hidden. There are some red dots somewhere that you can't perceive for sure. If you find them, great, but I don't expect you to see them. It doesn't scale, and this is less than 1 million data points. Is 1 million massive? Not really, right? So we are dealing with billions of records. No way. And even if we have a 10 million or 15 million pixel power wall like we have in Constance, like this has now like big and large resolution, this is like the 1 week, 5-minute interval data of the 100 most important internet ports on our university network. And let me zoom in a little that you get a feeling what you see here. This is like 1 day, 1 week, like you see the 7 days, and you see here, for example, a process that has high traffic over the weekend, Friday night to, in Europe, of course, Friday night to Saturday night, to Sunday night, and this is basically a backup process that is finishing over the weekend, right? This is a port that does some whatever backup traffic. Why is it not enough? We have not 100 ports, we have 65,000 ports, right? Every port may be interesting. What I show you is like a little percentage of what is out there at the data. And even this is already kind of, as you can tell, you have to walk around and look at it. So visualization alone doesn't work. And that's why we need visual analytics. And the following chart I have found in a book, in a similar chart, of course, about 20 years ago when I was starting my career. And basically, I kept it unchanged in my presentations. The computer is still a lot better in these domains. Maybe we have much higher errors here than 20 years ago. But there's still a lot to this part here. The general knowledge, perception, and creativity of the human is still unsurpassed by the computer. General knowledge, I think probably most of you agree. All the approaches that try to put general knowledge in the computer have failed to a certain extent. Some particular knowledge work. If you have a subdomain, expert systems have worked in subdomains quite well. But general knowledge in the sense that you can talk about everything, it's quite hard. And now,
what about Watson?
Yes, I was just about to refer to Watson. I was yesterday at IBM in Haifa and talking to some colleagues, and I've talked a lot with them and actually also read some of their books about the Watson. And if you have followed this thing, it was really, really interesting. It was basically capitalizing on this part here, having all the resources scanned in, all the data scanned in. And if you looked at some of the answers of Watson, they were really, really bad. If you think that they have general knowledge, you could really feel. The good thing that they had a scoring algorithm that was telling, I'm not giving a lot of money, I'm not setting a lot of money if I'm not that sure. And for the bad answers, they set a little money. So they knew that they didn't know it, but they didn't have general knowledge in the sense that a 7-year-old has. But of course, they were able to answer many of the questions because they had all these books scanned in and like all this knowledge, big data repository, which is basically just taking this to overcome the limited general knowledge. We wouldn't call it knowledge if somebody just had the big dictionary and can check out everything. If you give the human the ability to check out all the books, the human would still be better in that, right? So, and this is, I think, this part over this part, but we could discuss it in more detail. If you go for perception, I heard that they again did it as many times before for this new flight that was missing, the Malaysian flight. They did crowdsourcing of checking for debris by partitioning the satellite images and giving it out to the crowds to find the debris, distinguish debris from waves, which seemingly automated algorithms can't still do. Just one example, and they've done it before in many cases when Jim Gray was lost and Steve Fawcett were lost. They did the same thing because they couldn't do it by algorithms, distinguishing a little boat from waves or finding the lost plane of Steve Fawcett. They always did crowdsourcing because that was the only hope. So the perception of the human seems to be still unsurpassed in that respect. And creativity, I don't need to discuss, I hope. If you have an idea of how to define creativity on the computer, I'm happy to discuss it with you. I haven't found a good definition to even measure that, like art, music, when it's creative and when not, right? We may be able to discuss it. Maybe we consider computers to be creative, but at this point, I don't think there is even a good definition of creativity. But with all that said, I think what is clear, we want to combine the two to make it really powerful. Combine the strengths of the computer with the strengths of the human. And I like the quote of which is attributed to Albert Einstein very much. He's supposed to have said, computers are incredibly fast, accurate, and stupid. Humans are incredibly slow, inaccurate, and brilliant. Together, they are powerful beyond imagination. And this is basically the one-sentence summary of what visual analytics tried to do. It tries to combine these two things and empowers the human to really profit from the strengths of the computer in order to make good invention, good discoveries. And I was the scientific coordinator of a big EU coordination action, and the result of that coordination action is summarized in this book. You can download it from this webpage here if you are interested in reading it. What I want to show you briefly now is a little video clip that we put together, which is motivating visual analytics in this kind of, in a very, very, very general way. And I'm not showing the full video, we don't have that much time, but I will give you a little teaser so you can look at it at YouTube if you want to see it in full. I think I cut it off here because otherwise I won't get to my second part. I wanted to show you a few examples. Like, you can watch the whole video on YouTube, just type in Vismaster and you should be able to find it. And you get a little more, like it's only 10 minutes total, so it's like a little more on how visual analytics may work. What I want to show you now is at least 2 of these 4 domains that I was preparing for this presentation. I'll start with network security, and then I go a little bit into document analysis, just to give you a feeling of how visual analytics may work, may be applied, how these 2 domains can be brought together. And one comment before I start: visual analytics is not the right solution for every problem. If you have a fully automated algorithm that is doing the job, you may not want to bring the human into the loop. Like credit card approval. You have very nice algorithm, 99% accuracy is sufficient. Why should you do something with human involvement? But there are many problems, as I explained already, where you have no chance without the human in the loop, and for that you need visual analytics in addition to all the automated algorithms that you have. And this is what you should take away, and I want to exemplify that now with at least a couple of examples. Network security, and I'm now showing you some visuals. I'm not going into the details of the automated algorithms because we don't have that much time. So this is a tree map, as I explained before, and as you can see, this is now scaled. The size of these rectangles are scaled by the size, by the number of IP addresses that we get from these countries, and this is kind of dynamic, so the size depends on how many IP addresses are in the data set. As you can see here, North America gets about half of the ISP space. This is Europe getting about 1/4, and Asia getting 1/4, and South America and Asia, not Asia, but Africa don't get a lot, so it's like really not that relevant in the IP number of IP size of the IP space. And as you can see here, I already zoomed in to Germany. If I now blow that up, and of course I can go in any level here, I see now the IP map of Europe blown up here, and you see this is a special algorithm that is kind of trying to keep the relationships between countries and continents on the first levels of the hierarchy. On the lower levels, we don't have this like map type layout for IP addresses, subspaces, ISPs. You don't have that. The autonomous systems are the ISPs, the internet providers. For them, we have a linear ordering, which is going according to their IP subspace from the left upper corner to the lower right corner, and you see the big, the DFN in Germany and like the Telekom, German Telekom having the biggest IP space, but you see some small ones. Maybe you see that red dot here, a small one here that is also red. I can zoom in one more level so you see that a little better, I guess. There's a little red one, and this is due to like this university network data. We have installed our installation at the university gateway, capturing all the traffic at the university. And this is a cheap provider where the students have their accounts. So this is where they log in or go in and out. And that's a cheap provider that many of the students have an account with. And you can go into any level. This hierarchy, IP hierarchy, is like at least 32 bits. So you have 32 levels of this hierarchy that you can go into and can zoom in on any level. And the data is actually more difficult because it's not only, you can only show here incoming or outgoing IP address and aggregate by that. Actually, you do have connections between one IP address and another IP address. So you actually have lines between IP addresses. So it's a lot more complicated. If you plot them straight as straight lines, you don't see anything with any significant traffic. Even with just 1,000 lines, it's getting completely full the screen. So it's like no way to show it. And this is now already using a technique that is called edge bundling in order to get rid of some of the traffic. But what I want to show you now is an example of a visual analytics system. So what is a visual analytics system in that context? We wanted to support the university staff in trying to keep the network safe. So they have a commercial intrusion detection system that is producing alerts fully automatically. What you get from that is a list of intrusion detection alerts. Taking the traffic, getting the alerts. It's always a list, prioritized, and they always work off the top, as usual, and they never come down to the bottom of the list because more alerts come in. It's a streaming application, of course. So you have a long list with alerts, and you work off the top ones. And depending on how much stuff and time they have, they get maybe to the 10th record there, but usually not more, because then they have new alerts. What we do now, in addition, we capture the raw traffic, the net flows, and in order to do that, you have to work a lot with like streaming database. I'm not going into any details. This took my student a couple of years to implement this pipeline to have these records fast enough, get the aggregations done fast enough, and so on and so forth. And we work with Symantec. If you have never heard about honeypots, it's basically adding to the suspicious IP traffic by having computers in your network that are acting. They have no valid traffic. They just have simulate an open computer, and any traffic that goes to that machine is bad one. It's bad traffic. These are the only valid traffic are basically scans and other IP addresses that try to do something bad on that computer. This has no purpose, and Symantec has a network of hundreds of those worldwide. So what did we do? We wanted to bring this automated analysis together with the raw data by using visual analytics tools. And what we do, we visualize the raw data, we visualize the intrusion detection table, just make it a little nicer, help them to deal with it a little better. But the core is then the integration of the two, bringing the analytics together with the raw data and visualizing the interesting part of it. And then, of course, you can go to the details, looking at the host or net flow details. So just to show you an image of the interface, it's an expert system. It's not for everyday use, not for you using it at your own computer. And so you see a lot of stuff here that you can configure and use network administrator tools. But what you see here is basically the university network in the back as a tree map with the size corresponding to the number of machines. And the color meaning whatever variable you have selected here, traffic or whatever. And the external circles are the external nodes accessing our computer. And the algorithm that is behind this is basically what you take a part of your intrusion detection list and look at the traffic that generated this alert, and looking at the raw traffic of that data. And an algorithm is clustering these external nodes to the 4 sides of this screen by the similarity of their traffic into our network. And then what you see here basically, and you basically can see there are many nodes here which are accessing a few computers or a few subnets. And you can even see that while you have like these hundreds of lines here. You can see that, and guess what it is? Anybody in network security? Like an expert would say, oh, very clear, it's a distributed attack. Many computers accessing one machine, many external computers with a very similar traffic accessing the same machine. So everybody of these tried 5 passwords on this machine because they wanted to hack this machine because they found an open SSL port. And this is real data. This is not kind of, this happens every day on the university network, every day. And you would see also scanners that scan all the data and so on and so forth. So this is kind of giving you an example of, and these alerts are all low on the list, right? They never get down to, that's by design, right? The intrusion detection people, like they can't go for everything that is having just 5 packets to a computer or 5 IP flows. It's too little to go after it. But if you have like thousands doing the same thing, they still may hack it, right? So it's like kind of this trade-off. And if you put your thresholds down, they try even less. They do only 3 trials each. They take more computers to do it. So this is kind of a game. And here's a way of dealing with that and using a lot of automation, but combining it with visualization. And there are other tools I have no time to explain, looking at the temporal patterns here and other visualizations that help you to explore this data in a way. And we have put this all in an environment with, this is an environment where you have 3 high-resolution LCD displays, each of them having about 10 megapixels. And they are becoming cheap now because of the consumer market, with a touch table to control it. So we have this kind of a control room setup, which is really helping you a lot. You have a lot of screen space and can do a lot. So I have like 3 more minutes, so I can go into one more application. I'm just teasing you, hopefully, in getting into this domain of visual analytics and giving you a little kind of ideas what you could do if you combine the best automated tools that you can have with some advanced visualizations and interactive visualizations that can help you to explore the data. And I think I skipped this application, go right into some that may be relevant for business. So we did one application, and I'm skipping a lot here, but I don't have time. Customer feedback analysis. You know that companies are collecting customer feedbacks. You certainly had that coming up box, give us feedback, and you can write anything. I liked your service, I didn't like it, this went wrong, and whatever. Don't expect people to read it. Big company gets millions of those. And they don't have people to read all of them. Very simple. If it's a small company, they may read it. But if it's a big company, we work with a big company, they get millions of these customer feedback records. They still collect it, but they don't have time to read it. So what do? So far, a person was assigned to check out every morning, is there something new that I should know? They don't want to read what they already know. Many people complain about this, I know this is not what I want. So we devised a whole pipeline of automated things that you need to do, and you can look at the records if you are in text processing, you know some of it, right? You do a lot of, but finally you get down to feature detection. You detect certain features, you want to know what is new, and the sophisticated part of this is basically, where is it, like you do co-occurrence analysis. Terms that co-occur with other terms for the first time are kind of interesting indicators that something new happened. So basically you do in the end a pattern scoring, and the pattern scoring has several attributes that are important to distinguish interesting new patterns from patterns that you already know. And now I'm just showing you, I'm not going into all the details. There's lots of details behind this, which is by no means time to explain it. But what we want to do is now visualize these patterns to have the person quickly decide, do I want to read it or not? To read the right ones quickly. And what you see here is basically what you have is you have a timeline. And if you just show the messages over time, you may have many messages at the same time. But if there's a real problem, there will be lots of things at the same time. And then nothing happening on that particular topic for a long time, for that particular set of terms. So what we wanted to have a visualization that shows every customer feedback next to each other, but still have the time density. And what we did was basically having these time density curves underneath, which are showing whether these records are close in time or not. And of course, there are some statistics behind it, more likely distance. What you get is basically something like this. These are now the individual record. The color is the sentiment and so on, which are other parameters. But down here, you see, when it's up here, it means they were all very close in time. If there is 0 in between, you don't know how much time there was in between, which we don't care about, right? We only care about when it was close in time. That is, so here we have something happening that I may want to investigate. And now if you look at the real tool, you get proposals by the automated algorithms of topics out of your data stream. And now you get, basically, you can look at every topic, you get this timeline, which is this time density plot, showing all the relevant concerning to this kind of whatever terms you have here. And then you see there was something here that was dense in time, and now you can click on them and read a few of them to get the feeling of what it is. So I think you got the feeling. This is a tool. Evaluation shows we were able to find, like in a year of data, we found all the events that they knew that were happening in that particular year, like all the problems that they had, we were able to retrieve. But the good thing was we were able to find more additional ones. which they verified after the fact, but they didn't recognize by their manual reading. So they were really convinced that this is helping them. And of course, it makes their life a lot easier. Here, a few more examples where some things happened. One with password, one with packing lists. There was a problem with the packing lists. And this is all that involves packing lists, right? And so you get the feeling. So I have to come to a conclusion. I can't go into financial analysis, but let me conclude with a few remarks on visual analytics. There are lots of technical challenges. The main technical challenge, of course, is coming from the data, streaming data, complex structure, uncertainties, and applications have their particular problems. If you go for e-humanities and molecular biology, multimedia, you have always special challenges. And one of the challenges of visual analytics in working with industry is how to evaluate. I showed you in some cases you can show them and they are convinced, but in some cases, since the human is involved, there is not a number like 98% versus 97%. No, it's not. It's a lot more complex because the human is involved. But what we have to get to is, and this is what has been done before, visualization of the data, raw data, or visualization of the data mining results. What we have to get to is to something where we really tightly integrate the visualization with the data mining algorithm, with the separate steps of the algorithm, and show what is important in between. Really tightly integrated to get the human tightly involved with the algorithms. And this is still kind of trying to partition the algorithms in the right way, trying to find how to visualize this, how to best support the humans in doing this. This is kind of the only way to make progress in some of the domains that I was mentioning before. And I would like to conclude with a quote that is attributed to a person that lived a long time ago in the 16th century, but I think it's still true today. Galileo said, "All truths are easy to understand. Once they are discovered, the point is to discover them." And visual analytics is one technology that you need to discover new facts. Thank you very much.
There is kind of paradox with the visualization, because if you want to give good visual picture, you need to assume what people are looking for, what will draw their attention, what is interesting for them. But if you already know that, then you can create an algorithm that will filter out the interesting data. Because all the graphs that you showed us were created under the assumption that what's interesting is if there was a large number of unsatisfied customers in a close amount of time, right? So once you know what they're looking for, you can do it in other ways.
Actually, just to go back to that example that you just mentioned here, we have this complex algorithm that is like doing all these things, but it's a combination of many things. You see all these things go into the pattern scoring. And then you have all the other effects that you can't account for. Sentiment scores are never correct. You have all the semantic problems. So fully automated algorithm didn't work, basically. But what you have here is then an interface to go to the most important stuff very quickly and get very quick feedback. So we are not telling them this is what the algorithm would say, but maybe the first one the person already knows. So he wouldn't click on it, because I know that this occurred already previously, so I know what to expect, I know what people may talk about. But I haven't seen this one here, whatever shipping experience. This is new. Let me check it out. And then he may find out, oh, the scoring was wrong because somebody was writing an ironic email, ironic customer feedback, which we didn't get right? You don't get irony right in many cases. Even humans don't get it right always. But yeah, so there's no chance, at least that's what our linguists are telling us, getting irony is like 50% likelihood, so you better don't do it by an algorithm today, at least. So getting that is impossible. So some of these things are wrong that go into the pattern scoring. There's no way to do it correctly. And here we have an interface where the human can very quickly go into the things and discard some while going to others. So we are not basically, this is what the automated algorithm could do. And the automated algorithm would rank it exactly in that way. But the human is now going in and doing his kind of refinement of what the automated algorithm would do and kind of exploring that data, going to the right things very quickly and helping him to do a lot more than he was able to do before. And this was very convincing. They are using this tool in this company that we work with. So it's like helping them to deal with more data more quickly with less human resources. So I agree, you are right. If I know everything, then I can do it automatically. But in many cases, I don't know everything, and then I can still support the human.